Good morning, good afternoon, welcome. This is our Ask Tom session on mastering the match clause, a new SQL syntax for graph queries in Oracle Database 23C. I am Denise Myrick, and I'm here with Hans, and we are both product managers with the Oracle Graph and Spatial team. Thank you for joining us today. Hans, if you'd like to go to the second page.
Yeah.
So if you'd like to see any of our Ask Tom sessions on Graph, you can just go to asktom.oracle.com and search for Graph. Or you can follow this link here, and you'll be able to get these links when we post the session on asktom.com. If you have any questions at all during the presentation, please use the Q&A box. That will allow us to track the questions that we've answered. And if you'd like to reach out to Hans or I directly, you could use chat for that. So let's get started. Hans, what's a property graph and why would we use one?
So let's take a look at what property graphs are in the first place. Thank you, Denise, for the intro. Also, warm welcome from my side. Graph databases have actually become pretty popular over the last couple of years, right? I don't know if you've been looking into these technologies, and this time we haven't prepared a poll to explicitly ask who has already been looking into graph databases. But for those of you who are not so familiar with graph databases, they are different from relational databases in that entities are represented as what we call vertices, and their relationships, so the connections between these vertices, are represented as edges. It's kind of like what you see on the lower half of the slide here, right? Which means every row which you have in a customer table becomes a vertex, and every row in the cars table here in this little example becomes a vertex. And whenever there's a primary key foreign key relationship between the two, we create an edge, right? So essentially, this is the same data as before, but by handling the relationships as kind of first-class citizens in the database, what we are enabling is a new kind of analysis, right? And you can use that approach on structured data, like what we've shown here on the left-hand side, but this also works quite nicely on documents, right? So in a time when everybody and their dog is using LLMs on unstructured content, one typical approach in this is to extract entities from the documents, to extract relations from the documents, to extract co-references from the documents, and then turn that into a graph for further analysis, right? That was the little intro I wanted to give on the topic of graphs and graph databases altogether. Before we actually come to the SQL syntax, which is the main part of today's presentation, what I wanted to do is to go over a few typical use cases. And one more comment I have, which is, as most of you will know, right, Oracle is a multi-model database, and we've had support for like semantic web technologies in the Oracle database for ages, or since Oracle Database 10G release 2 to be precise. And we've added the property graph capabilities, which is what we're focusing on today, in 2016. Plus, we've made all of that functionality available without additional license cost in all editions of the database, right? And all the associated cloud services as well, right? Back in 2019. So to cut the long story short, if you have an Oracle database 12.2 or above, you can use the functionality that I'm talking about today, right? So functionality I'm talking about today is something you can use today in your environment. That's what I meant to say, right? Good. Okay, so much for the intro. Use cases. Just very briefly, right? Many of the customers we've been working with, they are actually using graph databases to model their data as a kind of network, right? So you can use that to organize or to structure your data from different operational systems, whether it be a data lake or a data warehouse, to form some kind of a knowledge graph, right? Like what we have here on the right-hand side, right? With the help of graph algorithms, you can then identify communities in that graph with similar properties or similar interests, for example. Or if you take the two customers in the middle here, if the customer on the right-hand side is someone who's new and sort of largely unknown, just by the fact that a well-known customer transfers money into his account, and that he's shopping at the same store as another connected customer, and he's looking at the same web pages and so on, you can conclude that there are similarities between these two customers on different levels, right? Which can either help you to be more specific in your marketing activities, or it can help you to derive a more accurate risk score or what have you, right? So that would be a kind of customer 360 type of scenario, or a knowledge graph, as some people say. Another typical pattern which we see involves analyzing hierarchies, right? So if you look at the manufacturing industry, for example, usually what you would find is these complex interlinked bills of material, right, for the different products or product variants, depending on which industry you're looking at. And graph databases, they're just very good at search or aggregation along those hierarchies, right? And they can help you to, for example, determine whether the parts in stock are sufficient to build a certain number of products. Or another typical use case in this domain will be to determine what would happen if a given part is not available. Say this guy here, right? If that one is not available, just by computing all higher level products with paths which end at that part would show you the impact, right? So that same approach is totally generic. You can use that for anything hierarchical. You can use that in financial services for Solvency II compliance, or you can use that in data lineage type of applications. GDPR is a typical thing, and so forth. Okay. Right. Also, identifying patterns is something which graphs or graph databases are pretty good at, right? Especially our customers in the financial services industry, they use this capability on large networks of financial transactions, right? Particularly if you want to identify suspicious behavior, if you want to identify fraudulent behavior, then graph databases are just great for identifying, for instance, circular money flows, which can be indicative of money laundering, right? Money starts at one account, goes through intermediate steps, and then lands back in the account where it started. Or another suspicious pattern is what we have here, right? Where rather than transferring money directly from the account on the top left to the bottom right, somebody is splitting up the money and transferring it through various intermediate steps, right? That is clearly showing that someone wants to obfuscate how the money flows, right? And that's not at all untypical of this type of scenario, right? The last use case, which I briefly wanted to touch on, is what we've got on this slide here, which is the use case of product recommendation, where if you take into account how customers are connected indirectly through products, you can get to a higher accuracy in your predictions, right? If you look at a e-commerce website under normal circumstances, where you use machine learning to look at which customer has purchased which product, not taking into account that somebody has a connection to someone else who has purchased another product, this will give you information which is then missing, right? So you can essentially improve your accuracy by taking into account the indirect relationships. That's what I meant to say at this point. Okay. So to cut the long story short, whenever you have data which you can model as either a network or as a hierarchy, and that's not only applicable to social networks, for example, then graphs are very powerful, especially if you are searching for indirect relationships, like in the case of paths here, or if you're looking for patterns. Okay, now the focus of today's session is on paths and patterns, right? So we will not be talking about algorithms in today's session. It's also not our plan to talk about visualization a whole lot. All of these things we'll cover in a future Ask Tom session. What we really want to drill down into today is how you find paths or how you identify patterns. Because if you want to do that, the first thing you need to do is to specify what you're looking for, right? And that essentially brings us to the topic of today's presentation, which is this, right? It is the new SQL 2023 standard. It is not particularly exciting to read, but the key thing is there is now a specification that defines how these paths or patterns should be defined in SQL, right? So it is an official part of the SQL 2023 standard. In fact, there's a complete new section on graphs or property graphs, to be precise, which is what we have here in that SQL standard, which was published in June of last year, right? The good news is with Oracle Database 23c, we have implemented that graph pattern matching in line with that standard, right? And in fact, we are the first commercial vendor that supports this standard, which is, by the way, also known as SQL PGQ.
Okay, so that's new. But you said we have support for property graphs since 2016. What did the previous implementation look like?
Okay, good point. So the previous implementation which we had was based on a query language that was similar to SQL, but it was not identical. It wasn't SQL as such. We'll see the difference in a bit, but the core part, which is what we'll be looking at in the next couple of slides, which is the match clause. The match clause is actually the same in both query languages. The other query language, by the way, being PGQL, the property graph query language, right? We'll look at that in just a sec. Thanks, Denise. That was a good question. And that brings us to a quick example. That example was actually a nice piece of work which I did together with, or which is actually based on what Kim Berg-Hansen from Seagull developed, and Kim and I, we jointly presented on that topic at Oracle User Group events. It is a kind of social network analysis example which we'll be looking at based on, I don't know if you know this, the 6 Degrees of Kevin Bacon game. If you don't know what that is, never mind. You can look it up on Wikipedia if you want. But the key thing is it is about actors who have been on the same cast of a movie with other actors who in turn have been on the same cast with other actors who in turn have been on the cast with other actors and so forth. And you're looking at these indirect relationships. What I mean is based on a data model which looks like this. Right? We started with a relational data model. In fact, we actually started with a text file with a long list of actors and movies, and we turned that into tables to start with. And by the way, SQL is just great as a tool for this type of exercise, right? Because it helps you to ingest the data very efficiently and then create the actual data model from that with all the great features which SQL as a language has and the scalability that the database brings along with it. But coming back to the data model here, what we have is essentially a data model that consists of 3 tables. We have the movies table, we have the actors table, and because between the actors and the movies there is an end-to-end relationship, right? One actor is typically on the cast of 1 or more movies, and typically also movies have 0 or more actors. So there's an end-to-end relationship, meaning we need to have if we have this implemented in third normal form, we need to have this intermediate table that resolves this end-to-end relationship into 2 one-to-end relationships. And that is our starting point if we want to figure out if an actor has been on the cast with another actor, what we need to do is to join the actors table to the cast members table, the cast members table to the movies table, and then back to the cast members, back to the actors. That is something which in the graph world is actually a bit easier, because there, if you represent the actors as vertices, like what we have here, every row in the actors table becomes one of these things, right? And every row in the movies table becomes a vertex as well, like here. Then you can look at the relationships between the actors through these connections, and already by visually inspecting the picture here, you can see how Kevin Bacon is connected as an actor through certain movies to other actors, right? Or if we have Kevin Bacon up here, here's a movie, Apollo 13 in this case, where also Tom Hanks was on the cast, and Tom Hanks was on the cast of Forrest Gump. So in Forrest Gump, he was on the cast with Michael T. Williamson. So there is an indirect relationship between Kevin Bacon and Michael T. Williamson, for example, through Tom Hanks. And these kind of four joins are represented as edges in that graph, right? So that essentially is our starting point. Right. Before we move on, anything in terms of questions? Maybe that's a good point to also remind you, do put your questions into the Q&A box. Then we can keep track of them. Or otherwise, I'll get confused pretty quickly.
So no questions from the audience, but I have a question. Can I create a graph of just actors and have the movie as a property on the edges?
That is actually a very good and very relevant question, because the graph databases are a bit different from relational technologies in that they are not as strict in the theory. Yes, you can essentially model things as anything. If, for example, like in this case, you have Kevin Bacon, and you would create direct connections between him and all of the other actors on the Apollo 13 movie, that would give you a bunch of edges, and it would essentially give a large number of edges, but it is pretty well possible. There's no reason why you would not be able to do this. It depends a little bit on the kind of query which you would like to use the graph for. Or there may be restrictions in the data model, which, for example, if you have a director on the movie as a new type of vertex and you add that one, then you would need to have a vertex explicitly for the movie. But otherwise, yes, you can have a graph which just consists of actors, and the movie information would just be held on the edge, which would also allow you to do the same kind of traversal. Good point. Good. Any other questions, anybody? If that's not the case, let me move on to how we would go from the relational model, the tabular model, to the graph. So technically, the way you express that mapping is in what we have here, in a create property graph statement, right? So in that DDL statement, we are now creating a graph called movies, which is based on two tables for vertices. We have the actors table, which gives us all the vertices which have a label actor and property name on that vertex, as well as the movies table, which has, and every vertex of type of that sort of coming from that table gets the label movie. And as a property, we have the title. And whenever there is an entry in the cast members table, then we are creating an edge which connects the actors, starting from the actors, because that's the source key, to the destination key, which is the movies, right? So this is essentially how we map the tabular data structures to the graph. And as you could see, this kind of end-to-end relationship with the intermediate table, that intermediate table goes away, just becomes an edge. And one more thing which is important to note is that we are not physically copying the data, right? This create property graph statement only creates metadata, which is why it's fast, and you don't duplicate the data, right? Now, if you're interested in all of the bells and whistles and so on for that create property graph statement, you can actually find that in the SQL reference manual. But I think that goes a little bit beyond what we wanted to talk about today.
So Hans, let's just pause. We have a couple questions in the Q&A.
Yep.
So the first question is, do we have a prediction algorithm in Graph 2?
So do we have a
prediction algorithm?
A prediction algorithm? Yes, indeed. We do have a whole library of graph machine learning or graph neural network type of algorithms which we have implemented. That is a topic which goes a little bit beyond what we wanted to talk about today. It is part of the graph server, which will be the topic of a separate Ask Tom session. But to cut the long story short, yes, we do have an implementation, for example, of the of a variant of the graph sage algorithm, and so you can predict. You can look for similarities in the graph depending on the environment of every vertex. You can look for patterns, and not only looking for exactly the same patterns, which is what we'll be doing today, but also similar patterns using these graph neural network type of algorithms. But that is a dedicated topic which we'll be happy to talk about in a different session. If there's a specific interest, we'll share our email IDs, Denise and I, at the end. So you can reach out to us if you have something specific which you would like to do. Shall we do that?
Sounds good.
Okay, more questions, or shall we move on for the moment?
We have 3 more questions. We have quite a few questions, actually.
That is nice. I like the interactive sessions. Go ahead.
Yeah. So earlier we had spatial and graph in Oracle Big Data Appliance. How is it different from graph in 23C?
Good point. So the graph server, which I was already talking about in the context of the algorithms, that is the same engine which we originally had on the Big Data Appliance, which of course has gone through a couple of iterations. It has moved on quite a bit since the time of the launch of the Big Data Appliance, but the core is the graph server engine. That is what we still have in the package for algorithms and sort of more advanced pattern matching queries, and we'll come to that in a second. What is new and what is completely new in 23C is that now the SQL kernel of the database understands graphs, meaning the property graph, which we create with the create property graph statement here as a DDL statement, is a regular Oracle database dictionary object. And again, we'll show that in a second. So all of the functionality which is now in the kernel of the database, that is new. That is something which obviously we didn't have on the Big Data Appliance because there was no database on the Big Data. There was no Oracle database on the Big Data Appliance. Okay.
Okay, great. And then one more question. How does Oracle store the vertices and edges? We already said that they were metadata. Are they built as relational tables? So the queries are syntax, which translates to a bunch of table joins, or have you been smarter with double linked lists, for example?
Okay. The answer is we've actually done both. In the core database, we are indeed storing the entities as rows in tables, and we've obviously we've done a couple of specifics down in the database kernel in order to handle the graph traversal in a reasonably fast manner. And you'll see how fast it is in just a moment when I show this in practice. That said, we do have our graph server, which dates back to what we already had on the big data appliance also, which does come with dedicated in-memory data structures, which is based on something like linked lists, which allow you to also do execute algorithms, which, as I said, is not the topic for today, which is where we benefit from these dedicated in-memory data structures and have support for all the parallelism and so forth. Right. I hope that, I mean, that's a relatively short answer to your relatively complex question. I think we'll leave it at that for the moment, because I still wanted to show you a few things in practice before we go overboard with the questions.
Okay, so the last two questions are going to merge, and I think your answer is going to be, we're going to get into this in a little bit. As there's no real direction, could we easily switch source and destination? And I think that they were referring to your last graph example. And then the next question was, is there a difference between creating directional versus undirectional graph?
Good point. Okay, good. And as you already said, we will indeed be seeing that in just a second. The edges do have directions, like here. I mean, we have a source. The source is always the actor. The destination is always the movie. So they are directed, and the direction is actually important for many use cases, while for others it is not. And I'll show you this in practice in just a second. In fact, that brings us nicely to the next slide, and I'll just move on to that and show you the match clause in practice, because I think from that it'll become clear very quickly. So if you look at the definition of patterns, the way we do this in the match clause is similar to what also other graph database vendors do, and this is exactly what the standard also prescribes. Is we are referring to everything that is a vertex by putting things into parentheses. So if I have a simple match clause like this one here, which says match, and then in parentheses M is of type movie, then it'll give me the two movies. Okay, so that would be a very simple match clause. Now that's a bit boring because it doesn't look at any relationships. If I want to have relationships like here, then I can come up with a match clause which says, find me all vertices of type actor, which are connected through an edge, and I just give it a variable name E here, to a vertex of type movie with the additional predicate of the m.title, the movie title is Apollo 13. What does that give us? That gives us all of these patterns. This is essentially 5 patterns of actor, edge, movie, actor, edge, movie, actor, edge, movie, with the additional predicate that the movie is Apollo 13. Okay, and as you can see here, the edge has a direction. If I change that to the opposite direction, then I'm not going to get anything, because these edges from movie to actor, they do not exist. There's none which satisfy this match clause. Okay, so I hope that answers the question we just had, and we can actually expand out from there and then have longer chains of vertex edge patterns, right? We have a vertex of type actor connected through an edge to a movie, connected through an edge in the opposite direction to an actor, and then again from the actor to a movie, and then again to an actor. So I have a long chain of vertices and edges with additional predicates. I can have as many as I want. Here in this case, I'm starting with the actor. So a.name is Kevin Bacon, and M2 title, which is the second movie which is in here, is Forrest Gump, right? That gives us a pattern which is relatively lengthy, right? And I'll give you an example, and maybe you want to pay attention because we'll do a poll in a second. This pattern, one pattern which satisfies this match clause is we have the actor Kevin Bacon connected through this edge to some movie, that edge to the movie Forrest Gump, which is sort of the second predicate, and then let's say Michael T. Williamson. That is one possible path. So 1, 2, 3, 4, 5 vertices and 4 edges in between. That would be one match, but that's only one match. Now, what do you think if you look at this match clause here? How many matches do you think you can find in that graph? We have a little poll which we've prepared. So Denise, can you? Yeah, excellent. Thank you. So that is great. All right. So how many matches do we have? What do you think? Is it one match, the one which I've already shown you? Is it 4 matches? Is it even 8 matches? What do you think? Come on, be courageous. How many matches do we have?
Hans, we have a
Okay,
question.
we have. Yes, go ahead. We'll answer the
yes.
question while folks are thinking about how many matches do we have. Yes, go ahead.
Actually, a really relevant question. So, is it possible to implement self-referencing nodes in combination with the node table partitions?
Self-referencing nodes are definitely possible. In conjunction with. Sorry, how did that work? I'm not sure I understood
in
the second half.
combination with node table partitions.
Node table partition. I'm not sure what node table partitions would refer to. You would have to. I mean, it's like standard hierarchies. That is something which you can easily implement in this kind of graph model also, and that includes self-references. No problem with that. So maybe I didn't quite understand the question. So maybe we can get back to that later, and then let me just briefly end the poll. And it's actually quite good to see that quite a few people came. And let me share the results so that you can see what we had. We had 80% of the folks said it's 4 matches. 20% said it's 8 matches. I actually have to admit I was in the fraction that said it was 4, and then I asked the database, and the database says no, it's 8. If you look at it, and then where's my stop sharing it. Where's my laser pointer? Let me see if I can go back to my laser pointer. There are actually 8 matches here because you go from here to here to here to here to there. That's 1. That's obvious. You have another one which goes down here. That's 2. Here's a match going at the upper part here, and then here that's 3 and 4. But what is easily overlooked is that a valid path goes from here to here to here to Forrest Gump, and then back to Tom Hanks, or from here to here to here to there. That's also a valid path, so that would be 6. And then the other ones are the 2 going up above here, right? So it is indeed 8 matches, just to let you know that these questions can actually be tricky. If you follow these paths, it is not always obvious how many results you end up with, and there are occasional surprises. Right. Okay, good. So thanks a lot for that. Did I share the results? Or shall we just remove the... Okay, did I share that? Okay. Yeah. Okay, stop sharing, and then we can get rid of the poll. Right, moving on, because we don't have a whole lot of time left, I have to say. So we were looking at the match clause here with the chains of matches, right? So this is the end result. Okay, let's jump on to the next. You can actually simplify that query a little bit, because we only have alternating actors, movies, patterns. So when we are starting with an actor, it's clear that the vertex here will always be a movie and that will always be an actor and so forth. So we can shorten that a little bit. So that'll give you the same result. You could think about removing the second predicate, the Forrest Gump, but that'll give you a different result. That'll give you all the edges. If you add the Forrest Gump again, then this brings us to the topic of undirected edges, right? That was the question we had previously. If we have an undirected edge, we can represent it just without the arrow, right? And that'll give us the same result as before. So it is essentially a simpler notation compared to what we had in the beginning when we had the poll. So ignoring the edge is something which is possible. And that's nice because then we can also use repetitive patterns. If we ignore the edge, we can say, okay, I'm looking for all patterns where we are starting with an actor at some vertex, in this case, again, Kevin Bacon, and then I want two consecutive edges, and then we're ending up somewhere else. And through two consecutive edges, we're always ending up at some actor, and that's designated by these curly braces. Okay, and so we could do the match thing again. How many matches we could do? We're not doing a poll this time, but how many matches do we have? We have all of the matches where Kevin Bacon is connected through 2 hops to another actor. Is it what, 4 results? Is it 5 results? It is, of course, 5 results because it could be from Kevin Bacon to here and then back to Kevin Bacon. So that is. And note one more thing, we're skipping the movie vertex here, right? There's no variable that gives us the movie vertex. Right. And we can, rather than having just 2 hops, we can say, make it 4 hops. So let's look at all the actors which are connected through 4 edges. And again, 4 edges will always end up at another actor, and it'll of course return the actors from the previous query. And there's one more thing which is also important. A2 here is a singleton variable because that is always per match. That's always one result. E here, the variable E, is a group variable, right? Each match, whenever we have a resulting match, that'll have 4 edges, right? Meaning if you want to do something with that variable, you'll have to use aggregations like sum or average or list ag or whatever, right? Okay, so that is one thing which gives you only the actors. And again, you could move back and forth, right? So you go from Kevin Bacon to here to back to forth and so on. 4 hops in sort of any direction back and forth gives you a lot of different options. Good. That almost brings us to the end because it brings us very close to pathfinding, right? We can use that possibility of the match clause with the repetitive edges to find connections between 2 vertices, right? If we specify starting point as Kevin Bacon and end point as Michael T. Williamson, then you can look for all matches where these 2 conditions are met. And you can see, okay, one's going up here and one's going down here, for example. So that gives us 2 paths with 4 hops. The results, they give you just the 2 vertices and the 4 edges, right? And then from counting the edges or from computing things along the edges, you can derive further information, like the distance here in this case, right? And we can look for shortest paths also. That doesn't. So this what I've just shown you, it doesn't only work with fixed length paths where I have to specify how many hops I do, but I can also specify I have 0 or more hops. And then together with the shortest clause here, you can look for the shortest path between the two actors, right? And you can whatever count the number of edges along the path or something, right? And again, E here is a group variable, right? Right, so that would give us that path, and as we are not able to access the movie in between if we just look at the repetitive pattern of being an edge, we can also specify a combination of edge and vertex and repeat that. Again, these would then be both group variables, and we can look for the shortest path, and then we can access the variable s and do aggregations along the path, like we could do a list ag along the path or something, right? So that we know which actor is on the way, or which actor and which movie is on the way. Good, right? So that would give us this path, because match shortest is actually resolved into match any shortest. As soon as I find a shortest path, I stop. Well, that's what the database does, at least. If I want all shortest path in case there's more than one shortest path, so if there are several paths of the same length, all of which are equally short, then there is the match all shortest, which you can use, right? And that'll give you sort of all permutations. And there's a bunch of additional variations which you can use in conjunction with the shortest path. However, before you try that on a 23C database, the shortest path implementation, that is something which is not yet available in SQL in 23C, right? That functionality didn't make it into the upcoming 23.4 release, but we are planning to include that in a later release update, right? And the same applies to the other language constructs which we have on this slide, like the cheapest path, where you can essentially associate a cost with each edge that you traverse, or the top K shortest paths, or the path options, right? Path options that allow you to select only acyclic paths where you don't, come back to a given point along the path, or paths that include cycles, but where the edges are not being repeated, and so on. And also what is not included is what we have at the bottom here, the one row per step clause that essentially retrieves all of the vertex edge vertex patterns along a path, which is important if you want to visualize things, right? If you want to use these constructs, you can actually do this today. You can do it on 23C, you can do it on 19C, or you can do it on 12.2, whatever you have, as long as you use the graph server, which I was mentioning earlier, right? Again, that'll be a topic for an upcoming session. Okay? Good. Any more questions, Denise?
We have two questions, but one I'm going to answer separately. But this one I think maybe people will be interested in. Does the syntax mean that nodes A, A2, and A3 are always different when they have different identifiers?
They don't have to be. Nope, they don't have to be. They can be repeating. In fact, you'll see that quite frequently. They would be repeating. You can filter out those cases where you have repeating vertices, which is exactly what we have here. If you look at acyclic paths, because then you would not be going back to a given point. These would be filtered out if you remove all the cyclic paths and leave only the acyclic paths. So these are things which you can do with these path options.
Thank you. And then, so we've seen how to define patterns using the match clause, but what does the actual SQL statement look like?
Yeah, actually, good point, because this was sort of slightly without context. The match clause, as I've explained it, of course, doesn't occur standalone. It is always part of a query, and the reason why I talked about it as a standalone thing was that the match clause is actually the same in the database kernel in Oracle 23C and in what we had previously in PGQL, right? So in SQL, the surrounding SQL query does look a little different because the database, at the end of the day, what it expects is a row set as the output from this pattern matching exercise. So what we need to do if we have this match clause and we found all our matches is we need to map this back to something which the overarching SQL statement, so the select statement in this case, understands, and that's what we use the columns clause for, which it does exactly that mapping. So we have a graph table function that emits a row set as we expect in the SQL clause, which also means that with the result you can do anything. You can have all your group by and you all the JSON capabilities and what have you. All of that is possible, and the mapping occurs through this columns clause. In PGQL, which is what we had previously, the syntax is a little bit different because there we are actually handling vertices and edges as native objects in graph server. But in PGQL, we have also implemented the same syntax because that is what the standard prescribes, the new SQL standard, SQL 2023. We've also implemented that in graph server. So with that, you can actually carry over things you are doing on a graph server to the Oracle database. And I've been doing a lot of talking now. I wanted to actually show you something in practice before we actually come to a close. So if we quickly move on to my little demo, now that you've seen all of the match clause variants, and I've given you a little bit of background on how this fits into the SQL syntax, you should be prepared to get your hands dirty and do these things in practice. And my recommendation, if you want to do this, is to use the LiveLabs workshops. I don't know. I hope most of you know that we have this wonderful platform, developer.oracle.com/LiveLabs. On that platform, there is a dedicated workshop on exploring operational property graphs based on the 23C free release. And that's nice because it comes with the full automation. It installs the complete stack and configures everything. So you have a 23C database in the end, of course. You have a no VNC console, SQL Developer, the old one at least, ORDS, even Apex, and so on. And what this looks like in practice is, let me see if I can share that with you. It is what we've got here. So this is the environment, right? You get a terminal window. You have your hands-on lab exercises, and you get the SQL Developer. And it comes with a little demo data set with bank accounts and bank transfers and so forth. So this is running on a 23C database, and as I said, the 23C database has property graphs as native objects, so they're a regular part of the Oracle data dictionary, and you can run your match clauses, your SQL statements on this bank graph. Now that's 1,000 vertices, 5,000 edges. That is tiny, so it's nothing for performance testing, but just to give you an idea of how this works. And in SQL Developer, you can then see, okay, we are supporting both PGQL property graphs as well as SQL property graphs, and here we have a SQL property graph in the database to work with. You could use PGQL actually also here if you had a property graph here in your SQL Developer, right? In the interest of time, I think I'm going to leave it at that, but I would strongly recommend that you take a look at that LiveLabs workshop. Good. So that brings us back to my slides. I hope you can see my slides, Denise.
Yes, we can, Hans.
Good. Excellent. Right. So let's move on then.
So one thing that you just showed is the SQL developer. How does it know about PGQL and SQL?
That's actually a very valid question. Because obviously SQL Developer is primarily for SQL, but what we've done is we have built a PGQL plugin that parses PGQL on the client side, translates it to SQL, and then runs SQL on the database. That would be the model which works on database 12.2 and above. If you don't have the graph server installed. So you can use PGQL natively on the database, even without graph server installed. And the way this works is it'll do the translation in the client. Obviously, in 23C, I hope it's become clear that property graphs are a native object in the database. And with that, they would be treated like like a view or something on top of your existing data. There's one thing which I wanted to emphasize here. If you don't use graph server, then you don't have all of the language constructs that we have with the graph server. You don't have the algorithms, for example, but at least the sort of the fundamental match clause that is available, right?
Isn't this confusing?
Yeah, you're right. I mean, to some degree, there is the risk for confusion, at least if you have, but only if you have existing graphs in a, let's say, 19C environment, for example, right? So from that perspective, it is something which is not necessarily straightforward, because the create property graph statement looks exactly the same no matter if you have a PGQL property graph or a SQL-based property graph. However, the metadata structures, which is why SQL Developer can distinguish them, the metadata structures are different. Right here, we have the user property graph view and things in the data dictionary. That's something we don't have here, and so forth. So you need to be aware of what you're working with. If you are working with graphs already in a 19C environment, let's say, our recommendation is that you would use the new PGQL 2.0 syntax with the graph table function, which I was showing on that slide a moment ago. And then if you make sure that you are only using language constructs that also the SQL engine understands, and if you're using the JDBC driver that we are that we're providing as part of the graph client, and then if you're also making sure that you're not using views, then you can actually carry over everything you've done on a 19C environment or a 12.2 environment to the 23C database. Okay, I hope that makes sense. And I guess we have to hurry up a little bit.
We do. All right, so we know that we can create a graph in 12.2, 19C, and 23C. And now we know how to use the match clause. But what's the benefit? Can't we use joins instead of pattern matching?
Yeah, very valid point. Of course, you could do things with joins, but if you look at that select statement here, so this pattern matching statement with the between 1 and 5 hops match clause here, if you wanted to translate that to SQL, you can do that. In fact, that's what we do if you use a 19C database and so on. However, the resulting SQL would be relatively complex, because essentially you need to have a recursive, single recursive statement for every one of the permutations of combinations of tables, and then you need to do a union all in the end. So depending on how many tables are involved, this can be pretty nasty. And if you compare that to the previous slide, it is pretty compact, easy to read, and easy to maintain. So that's really the main benefit for any SQL developer, no matter how much you want to do with graphs in the end, for anything recursive, for anything network-like, for any path queries and so forth, any kind of indirect relationships, it is advantageous to use this approach. Good point. So I actually wanted to spend a little bit of time on another example which I've prepared, but I think in the interest of time, we're just going to go over that very quickly. It is a little more sophisticated in that it's using 3 different entities, and I wanted to add a 4th one, which also includes a JSON column. Essentially, the create property graph statement is not terribly complicated. It is essentially, it always looks a bit scary, but because we sort of do all mappings in one go, but if you unravel that thing, it's actually not so bad. If we use that, we can actually do a couple of nice queries on this thing, right? Here in the data model, we essentially have a travel type of scenario, right? We have cities. City has 1 or more airports, and then between airports there are different carriers providing different services. So you have routes between airports. Let me quickly show you what that looks like in practice, and for that I have not used the LiveLabs environment, but I have used my Visual Studio Code because I like that a lot. The Visual Studio Code with the SQL Developer plugin, right? I have this was sort of the original create property graph statement. We have the airports table, the cities table, connections between airports and cities, right, located in, and the routes between airports labeled as route. That's essentially the basis to our queries, and then you can start doing all kinds of queries like find me all routes between all airports in the city of Hamburg, for example. Oh, hang on, my connection is gone. Okay, it'll need to reconnect first of all, and I am not 100%. I've been talking too much. Okay, here we go. It is reconnecting. That gives me the opportunity to have a cup of coffee, which is great. Let me. Okay. Oh, I think we're already there. We are. So these are the 2 airports we have in Hamburg. We can then do sort of pattern matches where we're looking for all airports that are connected to Hamburg Airport, where Hamburg is designated by the IATA code HAM, and you can look for all airlines connecting Hamburg and Heathrow and so forth, right? Now, the example which I really wanted to show you, which is a little more sophisticated, is this. I have a slightly extended version of the property graph, which I can create, and I can show you actually how fast that is, because it's just metadata. Boom, done. Right? That was quick. It is only metadata. I have now a new table called train connections, which I've added to the mix. And train connections has a column with all the details of the train connection, which is of type JSON, and we can make use of that by extracting JSON from that, JSON document, and using that as a property in every vertex, right? And then we can actually start running queries, and I'll save you the metadata. That is not so interesting. Here, for example, we have all connections between Paris Airport, which are train connections, right? The edge is of type train connection, and the result is that there are none because I haven't inserted any. So let's insert 4 train connections just for the sake of the example. 1, 2, 3, 4, commit, and then same query gives us all the train connections from Paris, so you can get to London, and there are 2 operators. Okay, so that is just the setup, right? Just so that you have an idea. If we now want to look at the connections between cities, that is an extra step. We have a vertex type city connected to an airport, which is connected through a route to another airport, which is located in another city, right? With the predicates. City is Paris, country is France, city 2 is London, country is United Kingdom, right? That gives us all the flight connections between airports in Paris, which is if you are traveling a little bit, this is Charles de Gaulle, Orly, and so on, connected to Heathrow, London City, London Gatwick, and so forth. So that gives you all the airline connections. And now I can, just by adding one small thing, by saying, okay, I'm not only looking at the routes, the airline connections, I'm also looking at the train connections. Now give me all the connections which are either airline or train connections. And that gives me a few more results. That gives me 12 results. And the reason why I wanted to show you this was on the path here between the airports, we now have different edges with different properties, right? For airline edges, we have the name of the airline. For train connections, we have the operator, right? And so this is how we deal with these schema flexible graphs. Okay, I think we're already a little over time. Let me just quickly wrap up. I think we are back to the slides, Denise, are we?
Yes.
Good. Okay, so we've seen the demo. The idea was to add a JSON object. You can either have a full JSON object as a which you can surface through the columns clause, or you just extract one element of the JSON document as a property. And that is nice because it gives you schema flexible graphs. And that was all I wanted to show you. And with that, I wanted to hand back to Denise for the summary.
Thanks, Hans. This was super fun, and I learned a lot from you today. Today we went over the fact that graphs have many applications, including analyzing direct and indirect relationships, which we just saw. You taught us about the SQL 23C standard, which includes this new section on graphs. We saw the match clause in action. We compared PGQL and the new SQL syntax. And you showed us a lot of benefits of the match clause. Here we can see some further information on Oracle Graph. We have a webpage on Oracle Graph, which was just revamped. There's plenty of videos on YouTube. You can, as Hans showed us, go through some LiveLabs if you search on graphs. We have a number of blogs, both on Database Insider and Medium.com. And of course, it's the documentation. And if you wanted to get started with all of this, Hans, what would you recommend?
Well, there's one thing which I would strongly recommend if you want to get started. I mean, here we were really looking at 23C, folks using SQL and so on. If you want to start working with graphs in general, my recommendation would be to use Graph Studio in Autonomous Database. Right, that is not yet running on 23C, but it comes with all the automation of the Oracle Autonomous Database. It has a lot of additional tooling. We've shown it in previous Ask Tom sessions. You can use the tools to model your data. You have a notebook-based environment to work with the data, to visualize the results. And of course, all of that sits on top of Graph Server, so on top of the Graph Analytics engine, which gives you the full pattern matching capabilities, including all the shortest path options and stuff, as well as the over 60 built-in algorithms. That would be my recommendation. And yeah, I think that brings us to the close. Also, thank you from my side. Thank you, Denise, for the nice collaboration on this. I hope it's been useful for everybody, and I apologize for running over because of all of the questions. Thanks again for your time. Any final words from your side, Denise?
Thank you so much, Hans. We did have one question that we didn't get to, and the person has left, but in case they catch the recording, I'd love to answer it. And I didn't know the answer to answer. Does the performance method execution plan AWR work the same way as AWR for relational tables?
Yes, it does.
Okay.
So the answer to this one for the time being is yes, it is. The things which we've implemented are happening one or two layers deeper in the kernel.
Great. So my apologies to that person for not getting to it earlier, but thank you so much for all of the questions, and thank you, Hans, for your time.